Okay, 2.37. We are given a particle in a square well, or infinite square well, and we have the initial wave function psi of x comma 0 is equal to a sine cubed pi x over a between 0 and a. And we're given a bunch of things to do. So we want to find a, we want to find the time-dependent wave function, we want to calculate the expectation value of x as a function of time, and also the expectation value of energy. To do all this, we're given the hint that sine and cosine powers can be reduced via application of trigonometric sum formulas to linear combinations of sine m theta and cosine m theta, with m being 0, 1, 2, etc., etc. So let's take this one at a time. Start by trying to find a. So to do that, we just normalize. So magnitude psi x comma 0 squared, integral from 0 to a in this case, has to equal 1. Add a dx here. So then what that means is that a squared times the integral from 0 to a of sine to the power of 6 times pi x over a dx is equal to 1. And typically at this point you'd already be done with the problem because you just plug this into a calculator and do it for you. But here, evidently Griffiths wants us to evaluate it by hand, which is significantly more painful. The way we do this is we use double angle formulas to reduce the power on the sine. So what I mean by that is that I can take advantage of the property that cosine of 2 times some value a is actually equal to cosine squared a minus sine squared a. And it's also equal to 1 minus 2 sine squared a. And it's also equal to 2 cosine squared a minus 1. So what I can do is I can take my sine to the 6th term, and I can recognize, okay, 1 minus 2 sine squared times pi x over a is actually, or actually in this case, we wouldn't reduce it to the power of 2, we would reduce it to the power of 3. So 1 minus 2 sine, let's see, yeah, sorry, 1 minus 2 sine squared pi x over a is actually equal to cosine of 2 pi x over a, which if I move things around, then I get that 2 sine squared pi x over a is equal to 1 minus cosine 2 pi x over a, which means that sine squared times pi x over a is equal to 1/2 times 1 minus cosine 2 pi x over a. And what we have here is sine to the power of 6. That's just sine squared cubed. So I just cube both sides of this, and I get this new integral, a squared times the integral from 0 to a of sine squared cubed, which is going to be, 1/2 cubed, which is 1/8 times 1 minus cosine 2 pi x over a cubed dx. And from here, I can just evaluate this out fully. So let's see. Let's do this in a different color. Let's start by evaluating the squared version. 1 minus cosine 2 pi x over a times 1 minus cosine 2 pi x over a. Doing this multiplication, this is going to give me 1 minus 2 cosine 2 pi x over a plus cosine squared 2 pi x over a. And if I take this and I multiply it by a third factor of 1 minus cosine 2 pi x over a, this is going to give me, let's see, 1 minus cosine 2 pi x over a, and then minus 2 cosine 2 pi x over a, plus 2 cosine squared 2 pi x over a. Is that correct? 1 minus cosine 2 pi x over a minus 2 cosine 2 pi x over a plus 2 cosine squared 2 pi x over a, and then minus cosine cubed, or no, hang on. This final term is going to be plus cosine squared 2 pi x over a minus cosine cubed 2 pi x over a. At this point, let's see, we can combine some terms. So this is going to equal 1 minus 3 cosine 2 pi x over a plus 3 cosine squared 2 pi x over a, subtracted by cosine cubed 2 pi x over a. At this point, we do the exact same thing, right? I can invoke this property once again, so I'm going to copy paste this down. And I'm going to say, okay, well, I can say that, let's see, cosine of 4 pi x over a is going to equal 2 cosine squared 2 pi x over a minus 1, or 2 cosine squared 2 pi x over a is equal to 1 plus cosine 4 pi x over a, or cosine squared 2 pi x over a is going to equal 1/2 times 1 plus cosine 4 pi x over a. So if I apply that over here, what this is going to give me is, let's see, 1 minus 3 cosine 2 pi x over a plus 3/2 1 plus cosine 4 pi x over a. Let's make the brackets square instead to make it neater. And then subtracted by 1/2 1 plus cosine 4 pi x over a multiplied by cosine 2 pi x over a. And at this point we can distribute out some things. So what we really have is 1 minus 3 cosine 2 pi x over a plus 3/2 cosine 4 pi x over a minus 1/2 cosine 2 pi x over a. Let's see, minus 1/2 cosine 4 pi x over a cosine 2 pi x over a. And at this point we can add some terms. So let's see, this is going to be 5/2 where I cancel out these two. Anything else? Minus cosine 2 pi x is over a. This is 7/2 cosine 2 pi x over a right here. And then plus 3/2 cosine 4 pi x over a. And then minus 1/2 cosine 4 pi x over a cosine 2 pi x over a. And if we remember what we were doing all the way up here, you know, we attached a 1/8 and multiplied, or had this integral attached. So what our real function states is actually a squared times the integral from 0 to a of 1/8 times everything. So I'm going to pull out the factor of 1/2, and it's going to be 1 over 16 times 5 minus 7 cosine 2 pi x over a plus 3 cosine 4 pi x over a minus cosine 4 pi x over a times cosine of 2 pi x over a. Close this off, add a dx. Let me just check that this is in fact correct. 5/2 minus 7/2 cosine 2 pi x over a minus sine 4 pi x. Plus 3/2 cosine 4 pi x. Yes, I do believe that is in fact correct. Yes, okay. So, let's see. Yeah. Okay, at this point, we actually have to do this integral. So the first three are pretty simple to do, and then the last one is a little bit more complicated, so let's do that one last and start by doing the first three. Okay, so this can be split into 4 different integrals. So this is going to turn into, let's see, the integral from 0 to a of, and I'm going to move the 1 over 16 out actually, of 5 dx minus the integral from 0 to a of 7 cosine 2 pi x over a dx plus the integral from 0 to a 3 cosine 4 pi x over a dx minus the integral from 0 to a cosine 4 pi x over a times cosine of 2 pi x over a dx. So doing these, let's see, this is going to be 5x minus 7 sine 2 pi x over a. Is that correct? Yeah, and then multiplied by a over 2 pi. And then plus 3 sine 4 pi x over a times a over 4 pi, all evaluated from 0 to a, subtracted by the integral from 0 to a cosine 4 pi x over a cosine 2 pi x over a dx. So at this point, let's see, evaluating this, this is going to give us 5a minus 7 sine of 2 pi times a over 2 pi plus 3 sine of 4 pi times a over 4 pi, and then subtracted by, let's see, 0 minus 7 sine 0 a over 2 pi plus 3 sine 0 a over 4 pi minus the integral from 0 to a cosine 4 pi x over a cosine 2 pi x over a dx. So let's see, immediately, sine of any even number times pi is automatically 0. So this is 0, this is 0. Similarly here, over here, sine of 0 is 0. So this is 0, this is 0. We're left with 5a minus the integral from 0 to a times cosine 4 pi x over a cosine 2 pi x over a dx. At this point, let's see, if we move the a squared over 16th back in, what we're going to get is, let's see, a squared times 5a over 16th minus a squared over 16th integral from 0 to a times cosine of 4 pi x over a times cosine 2 pi x over a dx. And here, at this point, we can use double angle formula to solve this final term. So we can recognize, and I'll write this in red, that cosine of 4 pi x over a is equal to 1 minus 2 sine squared 2 pi x over a. So I can sort of do that, and I can use u sub. So if I do that, then what I'll get is that, a squared 5a over 16th minus a squared over 16th times the integral from 0 to a of 1 minus 2 sine squared 2 pi x over a times cosine 2 pi x over a dx. Let's bracket this off properly. And at this point, I can use u sub, because if I recognize that, u is equal to 1 minus 2 sine squared 2 pi x over a, or sorry, apologies, if I recognize that u is equal to sine of 2 pi x over a, sine 2 pi x over a, then I can recognize that du is just equal to cosine 2 pi x over a multiplied by 2 pi over a, and add a dx here, so that means dx is equal to du over cosine 2 pi x over a multiplied by a over 2 pi. So if I substitute this in, this is going to give me a squared times 5a over 16 minus a squared over 16 times the integral from 0 to a of 1 minus 2u squared, and then times, let's see, du, the cosines cancel out, so a over 2 pi du. So if I actually do this integral, then a squared 5a over 16th minus a squared over 16th times a over 2 pi, and then u minus, let's see, 2 over 3u cubed, going from 0 to a. If we convert u back, then we get a squared 5a over 16th minus a squared over 16 times a over 2 pi multiplied by sine 2 pi x over a minus 2/3 sine cubed 2 pi x over a, evaluated from 0 to a. And here, recognize, if we plug in a, then we get sine of 2 pi in both sides that both go to 0. If we plug in 0 for x, we get sine of 0 and sine of 0. Also, both go to 0. So this entire term down here is also equal to 0. So what we're left with is just a squared 5a over 16th is equal to 1. So that means a squared is equal to 16 over 5a, or a is equal to 4 over square root of 5a. And we have found the normalization constant. Okay, now that we have a and we have the general form of psi of x comma 0, we can go on and try to find psi of x comma t via Fourier's trick, as we've done so many times before. So we're going to impose the standard condition, which is that any psi of x comma t can be expressed as an infinite summation, n equals 1 to infinity, of cn psi n phi n, for a given infinite square well function. Then we could recognize that if we set t equal to 0, then all the complex exponentials in phi go to 1, and we're left with a summation from n equals 1 to infinity of cn psi n. Then we can plug in any arbitrary psi of x comma 0 for this, including what we just found because of completeness theorem. So we get 4 over the square root of 5a times sine cubed pi x over a is equal to the summation from n equals 1 to infinity cn psi n. Then we take advantage of the fact that there's orthogonality between the individual infinite square well wave functions. We multiply psi m onto both sides, and we take the integral from negative infinity to infinity, or in this case from 0 to a. And what will happen is that all of the cn terms will cancel except for the one where n equals m. So cn is going to equal the integral from 0 to a of 4 over square root 5a sine cubed pi x over a times psi n dx. And technically, at this point, we're done. Because this does give us a general formula for cn, and then we can recognize that psi of x comma t is just going to be cn psi n phi n. And we know the general form for psi n and phi n, so we're done. However, there actually is room to go a little bit extra here, and the reason why I'm saying that is because right now we just know the general formula for cn, but we don't know if actually the cn terms go to infinity or not. We don't know if this summation is going to be an infinite summation, or if psi of x comma t is actually a finite sum, and cn only goes up to some certain value before sort of terminating and going to 0 for the rest of the higher indexes. This is normally we wouldn't be able to tell, but here the fact that psi of x comma 0 is equivalent to a cubic of sine, and the fact that the base wave function for the infinite square well psi n is based on sinusoids sort of seems to suggest sort of the fact that it's similar enough that maybe it's not actually 0. So once again, you don't have to do this. Technically, you've already finished the problem, but if you want to go the extra mile, you can test this out by trying to sort of decompose the sine cube term into complex exponentials to see if we can actually get it into the form of the infinite square well solutions, to see if the cn terms actually index up to infinity or not. So what I mean by this is I can recognize the fact that sine cubed pi x over a can be rewritten as a complex exponential, and I can rewrite this as e to the I pi x over a minus e to the negative I pi x over a over 2I, and I can cube this. So if I cube this, what I'm going to get is, let's see, this is going to give me e to the I pi x over a, whoops, subtracted by e to the negative I pi x over a, multiplied by e to the I pi x over a, subtracted by e to the negative I pi x over a. If I want to do the squared version of this, this is going to give me e to the 2I pi x over a, let's see, minus 1 plus e to the negative 2I pi x over a, or just e to the 2I pi x over a plus e to the negative 2I pi x over a minus 2. And then if I multiply this by another term of e to the I pi x over a minus, minus e to the negative I pi x over a, what is this going to give me? This is going to give me e to the 3I pi x over a, minus e to the I pi x over a, plus e to the negative I pi x over a, and then subtracted by e to the negative 3I pi x over a, and then finally minus 2e to the I pi x over a plus 2e to the negative I pi x over a. Is that correct? E to the 3I pi x over a minus e to the I pi x over a plus e to the negative I pi x over a minus e to the negative 3I pi x over a minus 2e to the I pi x over a plus 2e to the negative I pi. Yeah, okay, that's correct. And then 2I cubed is just going to give me, you know, negative 8I. So what I'm left with is that, you know, psi of x comma 0 is actually equal to a multiplied by this expression, which is going to be, let's see, immediately, is there anything I can combine? So this is going to be e to the 3I pi x over a, and then let's do I next. So this is going to be minus 3 e to the I pi x over a, and then plus 3 e to the I pi x over a, or e to the negative I pi x over a, and then minus e to the negative 3 I pi x over a. Is that correct? Minus 3. Yeah. That should be. Yeah. And then at the bottom, we're left with negative 8I. So let's see. We can split this up immediately, because if we recognize that this is actually equal to a times, let's see, e to the 3I pi x over a minus e to the negative 3I pi x over a, and then minus 3e to the I pi x over a plus 3e to the negative I pi x over a, and then I can recognize that this is equal to, let's see, move the negative out in the front, and I can multiply this. This is move out of 4, and this is going to give me a 2i at the bottom, and hopefully you see what I'm trying to do here, is I'm splitting this into two new sinusoids. So if I do this, then this is going to give me that this is equal to, let's see, let's move the minus back in for now. Well, actually, let's move it at the front for now. Negative a over 4, e to the 3I pi x over a minus e to the negative 3I pi x over a over 2i, and then added with negative 3e to the I pi x over a plus 3e to the negative I pi x over a over 2i. And then, let's see, I can turn this into a subtraction term, in which case this becomes positive and this becomes negative. And I can move this around. This is going to give me a over 4 times 3e to the I pi x over a minus 3e to the negative I pi x over a over 2i. And you know what? In fact, let's move the 3 to the front as well. And then we're going to subtract this by e to the 3i pi x over a minus e to the negative 3i pi x over a over 2i. And at this point, we just have two sort of sinusoids represented as complex exponentials. This is just going to equal 3/4, and let's multiply the a at the front. So 3/4 times sine pi x over a, subtracted by 1/4 sine 3 pi x over a. And at this point, this is just going to equal, you know, a times 3/4 sine pi x over a minus a over 4th sine 3 pi x over a. And remember that this is equal to psi of x comma 0. So at this point, we can look back on sort of our infinite square well and realize that sort of the infinite square well wave functions are just sinusoids. So let me pull those up. Yeah, so we can recognize that in red, psi n of x is equal to square root of 2 over a times sine n pi over a times x. And this is for the infinite square well. So, you know, square root of a over 2 times sine nx is equal to sine n pi x over a. So actually psi of x comma 0 is equal to a times 3/4, and then square root a over 2 times psi 1 minus a over 4 times square root of a over 2 times psi 3. So what's going to happen is that this is equal to c1, this is equal to c3, all of the other c terms are equal to 0, and we're effectively done. Okay, the next thing we want is the expectation value of x as a function of time. So instead of doing the traditional thing of just jamming it in between psi and psi star, we actually have to find psi of x comma t and define it that way. So what we can do is, you know, we already sort of recognize the fact that psi of x comma 0 is just this, so we can just apply sort of the time dependency onto it directly by attaching phi to each of these. So we can recognize, well, first off, okay, let's get the a out of the way. So this is equal to 4 over the square root of 5a times 3/4. Actually, you know what? It might be easier for me if I multiply the a last, just to save myself the trouble of having to deal with that square root for now. So instead of that, I'm just going to recognize that the time-dependent wave function is phi n being equal to c times e to the negative I over h bar times et. And what I'm going to do is I'm going to absorb the c into the a term, because they're all constants in the end. And what we're going to get is that this is going to be equal to, recognizing the fact that, you know, for an infinite square well, en is equal to n squared pi squared h bar squared over 2ma squared. This is going to equal e to the negative I t over h bar times n squared pi squared h bar squared over 2ma squared. Cancel out one of the h bars. This is going to give me e to the, let's see, e to the negative I n squared pi squared h bar over 2ma squared times t. So in that case, psi of x comma t is going to equal a. I'm going to pull the a out, and we're going to get, let's see, 3/4 square root a over 2 psi 1 times e to the negative I n squared pi squared h bar over 2ma squared times t. And in this case, since n is equal to 1, it's just pi squared h bar. And then we're subtracting by 1/4 times the square root of a over 2 times psi 3 times e to the negative I times, this time it's n is 3, so it's 9 pi squared h bar over 2ma squared times t. Recognize that, psi n can be related to sort of the infinite square well wave functions, so we can recognize that, let's write this in red. Psi n is equal to the square root of 2 over a times sine n pi x over a, which means that square root of a over 2 times psi n is equal to sine n pi x over a, as we've defined earlier. So this means that psi of x comma t is going to equal a times 3/4 times sine n pi x over a times e to the negative I pi squared h bar over 2ma squared times time, subtracted by 1/4 times sine of 3 pi x over a, and I just realized the n is supposed to go to 1 here, my apologies, and then e to the negative I times 9 pi squared h bar over 2ma squared times time. And now we do the doozy of multiplying this by the complex conjugate, which is going to give us, psi star of x comma t is going to equal a times 3/4 sine pi x over a, e to the this time instead of negative is going to be positive I because it's a complex conjugate. So positive I pi squared h bar over 2ma squared times time minus 1/4 sine 3 pi x over a, e to the positive I 9 pi squared h bar over 2ma squared times t, and then we can recognize that the expectation value of x with respect to time is going to equal the integral from 0 to positive a of x times psi x comma t multiplied by psi star x comma t. So now it's just a matter of multiplying this doozy of a function together. Okay, here we are on sort of the worst part of this problem. So I'm going to start off by distributing out 1/4 for all of these terms. So this is going to be 3, this is going to be 1, this is going to be 3, this is just going to be 1. I'm going to move the 3 down to make this a little bit neater. Okay, so this is going to be equal to a squared over 16 times the integral from 0 to a multiplied by x times, oh boy, okay, multiplying these together we get 9 sine squared pi x over a, the exponentials cancel out to 1, then subtracted by, let's see, uh, 3 sine pi x over a sine 3 pi x over a times e to the, oh god, okay, what is this going to be? 8 pi squared h bar to ma squared, I at the front, t, because this is going to be 9 over halves minus 1/2. So this is, yeah, I'm not going to simplify this for now because I don't want to touch it any more than I have to until I at least get everything else correctly. So this is going to be subtracted by 3 sine pi x over a sine 3 pi x over a multiplied by e to the, this time it's the opposite, negative I 8 pi squared h bar over 2ma squared times t, and then finally plus sine squared 3 pi x over a dx. Is that correct? Yes. Okay. So hopefully, sort of you remember what we did last time in regards to these. So we can sort of recognize that this is an integral of a psi1 function multiplied by an integral of a psi3 function, right? Because sine, and what I mean by this is that, sine pi x over a sine 3 pi x over a is sort of analogous to some constant c at the front multiplied by psi1 multiplied by psi3. And we remember, or hopefully you remember sort of the concept of orthogonality, which is that taking an integral through all of the valid space, which in this case is from 0 to a, because it's an infinite square well, of psi n times psi m star, where n and m aren't equal, is always going to result in 0. And we can recognize that since this is a dx integral, the complex exponential time-dependent term doesn't play a factor here. And also the fact that since the x, or the position-based wave function is real, psi3 star equals psi3 and psi1 star equals psi1. So because of that, automatically, these two middle integrals just go to 0. And just to make this more clear, the integral from 0 to a of psi n psi m star dx is equal to 0 if n doesn't equal m for any stationary state. In this case, we're using the stationary states of an infinite square well, and we can recognize that since the x-dependent wave function psi of x, little psi of x, has no imaginary dependency, its complex conjugate is going to equal its real component. So this directly substitutes into here. And because of that, these two middle terms just go to 0. What we're left with is that the expectation value of x is equal to a squared over 16 times the integral from 0 to a, times x times 9 sine squared pi x over a plus sine squared 3 pi x over a. Close this off with a dx, and we have two different integrals, and we have to solve this by sort of, how do I say this, by using the double angle formula. So let's see, we can recognize that 1 minus 2 sine squared of any value is equal to cosine of twice that value. So let's see, 1 minus cosine 2a is then going to equal to sine squared of a, or sine squared of a is going to equal 1/2 times 1 minus cosine 2a. Substituting in the values here, we get that for 1, sine squared of pi x over a is going to equal 1/2 times 1 minus cosine 2 pi x over a, and 0.2 sine squared 3 pi x over a is going to equal 1/2 1 minus cosine 6 pi x over a. So this is going to give us that the expectation value of x is going to equal a over 16 times the integral from 0 to a of x times, let's see, let's do distributive property as well. So 9 halves minus 9/2 cosine 2 pi x over a plus 1/2 minus cosine 6 pi x over a dx. This is going to give us there's supposed to be a squared term at the front. I completely forgot. A squared over 16 times the integral from 0 to a x of, let's see, is this correct? 9 halves plus 1/2. Yeah, so that's 10 halves. This is going to be 5 minus 9 halves cosine 2 pi x over a minus cosine 6 pi x over a dx. And what we're left with, if we split this integral into 3, a squared over 16 integral from 0 to a 5x dx minus integral from minus 9 halves integral from 0 to a of x times cosine 2 pi x over a dx, and then minus integral from 0 to a of x times cosine 6 pi x over a dx. close that off, and now it's just a matter of doing all three of these integrals. Okay, let's work on u sub now. So let's see, u is equal to x, du is equal to dx, dv is equal to cosine 2 pi x over a dx. So that means v is equal to sine 2 pi x over a times a over 2 pi. Similarly, u is equal to x, du is equal to dx, dv is equal to cosine 6 pi x over a times dx, and then v is going to equal sine 6 pi x over a multiplied by a over 6 pi. Then we use the integration by parts to evaluate these. So this is going to give us, let's see, start with a squared over 16 at the front. We get 5 halves x squared, which becomes evaluated from 0 to a. So this is going to be 5 halves a squared, subtracted by, really make this clear, this is a 9. 9 halves times the integral from 0 to a of, or sorry, 9 halves, and then multiplied by the integration by parts term. So uv, which is going to be, oh god, okay, I'm going to need a higher order of bracket to contain everything here. Now let's write this as red as well. So let's see, a over 2 pi times x sine 2 pi x over a evaluated from 0 to a. Immediately I see, you know, at a we have sine of 2 pi, and at 0 we have sine of 0, so automatically those always equal 0. So this is just, it just goes away, the border term. So it's uv minus integral v du. So negative integral v du, which is going to be negative integral from 0 to a over 2 pi sine 2 pi x over a times dx. And then subtracted by, and let's do the next one in blue. So we have uv again. Immediately I see, because it's evaluated from 0 to a, at x equals a, we get sine of 6 pi, which is 0, and x equals 0, we get sine of 0, which is 0. So uv vanishes, minus integral v du, so minus the integral from 0 to a of a over 6 pi times v du, sine 6 pi x over a times dx. And then we close this integral, we close everything off. So what we're left with is a squared over 16 times 5 halves a squared plus 9a over 4 pi integral from 0 to a sine 2 pi x over a dx plus the integral from 0 to a of, let's do a over 6 pi at the front, sine 6 pi x over a dx. And hopefully you see the same pattern here immediately, no matter how we don't even have to evaluate this, because we know that the answer is going to contain the same, actually wait, no, sorry, I'm an idiot. That is not true, ignore that statement. This is going to give us a squared over 16 times 5 halves a squared plus 9a over 4 pi. And let's add a higher order of bracket once again, because we need it here. Let's see. This is going to give us negative cosine 2 pi x over a times a over 2 pi evaluated from 0 to a. Is that correct? Yes. And then plus a over 6 pi times negative cosine 6 pi x over a times a over 6 pi. Going from 0 to a. Okay, this is going to give us a squared over 16 times 5a squared over 2 plus, let's see, 9a squared over 8 pi squared at the subtraction term cosine 2 pi x over a, going from 0 to a, and then minus a squared over 36 pi squared cosine 6 pi x over a, going from 0 to a. Okay, now we can expunge this out. So this is going to be cosine 2 pi minus cosine of 0, which is actually just equal to 0. Over here we have cosine of 6 pi minus cosine of 0, which is once again just equal to 0. 1 minus 1. So these latter two terms just go away, and we're conveniently left with a squared over 16 times 5a squared over 2. We know what a is. Originally we found a to equal 4 over the square root of 5a, so a squared is equal to 16 over 5a. So what we have is 16 over 5a times 5a squared over 16 times 2. The 16s cancel, the 5a cancels with the 5 and the a, and we're left with a half. So the expectation value of x with respect to time is actually independent of time, and it's equal to a over 2. Okay, finally, we want the expectation value of the energy, and this is so easy it might as well be trivial. We could recognize that, this is C1, this is C3, and we also know that the energy values for the infinite square well are equal to n squared pi squared h bar squared over 2m a squared. So if we then add in the a, then okay, C1 is equal to 4 over the square root of 5a multiplied by 3/4 square root a over 2. So this is going to give us, let's see, the square root of a cancels the square root of a at the bottom, so we get 3 over the square root of 10, and then C3 is going to equal negative 4 over square root 5a times 1/4 times square root of a over 2. The a's cancel, the 4's cancel, we get negative 1 over root 10. Then we can recognize that the probability of being in any given sort of stationary state when we measure a combination is going to be equal to sort of the magnitude squared of the c terms as we've determined way earlier on back in chapter 2. So we get that the probability of being in E1 is equal to magnitude C1 squared, which is going to be 9 out of 10, and the probability of being in E3 is going to be magnitude C3 squared, which is going to be 1 over 10. So finally, we get the average expectation value of the energy is going to be E1 times P1 plus E3 times P3, which is going to be pi squared h bar squared over 2m a squared times 9 over 10 plus 9 pi squared h bar squared over 2m a squared times 1 over 10. So this is going to give us, let's see, 18 pi squared h bar squared over 20m a squared, which is going to be equal to 9 pi squared h bar squared over 10m a squared. And that is the end of this problem.